Welcome to the PLC Professor's Workshop. We are in the last major project in the manual, and this is for what we call the virtual machine. We've already spent 2-3 lectures talking about it. In the last lecture, we actually got into talking about the process, the sequence. In this lab project, we're going to discuss the first method that almost everybody uses to write a sequential program, and that's using latches and unlatch. But as you will discover, when you use latches, you have to unlatch the whole world, meaning that you just keep latching up stuff, and eventually you're going to have to unlatch it. So we're going to start out with the easiest programming method. Latches and unlatch is the easiest to write, but more difficult to troubleshoot and make changes to. But we're going to start there, and then we're going to keep going through different methods. But this lecture will primarily be just on latch and unlatch. Let's do this. Okay, so in our last recording, we did the virtual devices. And in this case, the only virtual devices we're going to use in this process, in this virtual machine, is the virtual cylinders. We're not going to do virtual motors. It's just too straightforward. We turn a motor on. We don't need logic to simulate it getting up to speed. Now, in a more complex, like a factory acceptance test where you want to test out your code, maybe you need something like that, but not here. Let's not complicate this any more than we have to. We will start by reviewing the virtual machine and then continue on in the project manual. If you just finished the other recording, the previous recording, then you just listened to a couple minutes discussion on this virtual machine. But giving you the benefit of the doubt that you may have let a day or two get in between, we'll go through this again real quick. The green call out at the top, raw stock from upstream. So parts come in on the top of this diagram. You're looking down on the process. It has 5 cylinders. Now remember, we're using the virtual cylinders that we already created, which gives us a reaction of energizing the solenoid and then a delay before the extend proxies are made, and vice versa. When we de-energize the solenoid and the cylinder retracts, and then there's a delay, and then we get the retracted proxies. So part comes in. Once it's in the view of the barcode reader, the process doesn't know it's there. When it hits the optical path of photo I1, the barcode reader scans it, and then your logic will determine whether you're going to let it slide on through and out the bottom of this diagram, out on the feed conveyor to the next whatever's downstream, or are you going to push it out off the conveyor with cylinder 2 and into the workspace. And so photo I2 sees that it's there, and if it needs a hole drilled in it, then cylinder 1 extend. When the proxies are extended, fires up the drill motor and drives it in. Cylinder 4 drives the drill motor and bit into the part, and once it's in there, it stays a moment to auger out the debris, retracts, and then the part is basically finished in the workspace. So you retract cylinder 1 and 2, and now you push it out with 3 under the finished product conveyor, and then retract cylinder 3. Finished product conveyor comes on, the part moves down until it hits photo I3. It extends cylinder 5. When Prox 9 sees that the cylinder is extended, then it turns off the conveyor. That's simple. Now we'll convolute this as best we can as we go, but that's a quick review on this virtual machine. Taking the logic as we need it, the first step was to acknowledge a part coming in on the feed conveyor, or rather to sense that there was a part present. And remember that photo I1 is primarily used to trigger the barcode reader. Now we don't have a virtual barcode reader yet, but if you look at the logic here, it says if photo I1 senses a new part, then we begin incrementing a timer data type called barcode trigger pulse for a length of 1 second. We're using the timer timing pulse to set the virtual output bit, local 4.0 data.0, that we're calling barcode trigger. So that bit would be looked at in other logic that would trigger the barcode reader, and then the barcode reader would fill in a value for part number. And if the part number is greater than 5,000, then we latch a bit, which basically we're going to use that bit to say if that bit is latched, and as the part continues into the system, we want to pull it out and bore a hole in it. So I'm going to execute this logic. It's really so simple, it's probably not necessary. I'm going to leave the part number, I'm going to make it less than 5,000, but not 0. So in other words, that greater than instruction will not be true. So if we make sure everything's off here, I'll trigger the photo eye, and you see there was a 1 second pulse there on the barcode trigger, but we did not latch station 1.1. We'll make that something greater than 5,000, and we'll do that again. And I don't have to hold it down for the full second. All that I need is a real short pulse. You didn't even see it, right? That's how short it was. Because we don't need 1 second. This is what I call a pulse stretcher. Now in our logic, if this is on for 1/5000th of a second, and we don't have this timer in here, it's still going to turn on that bit, and if it's greater than 5,000, latch that bit. I'll clear that. But in the real world, that trigger pulse would need to propagate to the barcode reader. The barcode reader would have to react to it, trigger, and then send a value back to the system for part number. So that's why we have that 1 second in there. It's a pulse stretcher. So I'll do that again, but I'll leave it on long enough for you to see it doing something. Okay, all that gives us is station 1.1. That's the bit that says, hey, there's a part coming down the feed conveyor, and we want to perform an operation on it in this station, and that's all that it does. Okay, the first rung of logic, it latched a bit, station 1.1. We reserve station 1.0 for some sort of a preset condition. So really, station 1.1 is the first bit latched in the sequence. If that bit is on, then when the part arrives at photo I2, remember the part came in, hit photo I1, triggered the barcode reader, the value was greater than 5,000, now it shows 0. What you don't realize is later on we're going to clear that part immediately after we decide if we like it or not. We don't want to leave that part number in there. I'll put it back in for right now, just so you don't feel lonely. Now, station 1.1 was set. Now remember that part is traveling on the feed conveyor and has to travel at least a couple feet, so that's at least a few seconds or so. And when it hits photo I2 right here, and that's local 1i data 1, which is an actual input. So I'm going to turn that on, and immediately it tells cylinder 1 and cylinder 2 to extend. Now if the logic's working correctly, which it does not appear to be, after whatever the virtual cylinders have for delays for extending, these 2 bits will come on. So let's go look at the cylinders, and I see exactly what's wrong. I'm not executing the cylinders routine. I mean, this looks okay, it looks like it's running, but it's not. Remember, we have 5 cylinders in here. However, it's in the cylinders routine. In the main routine, we do not have a JSR, jump to subroutine instruction, to actually execute those. So I'm going to double click here, type in JSR, and then of course there is only one routine to pick from, even though it's going to show the main routine and cylinders. And now, as soon as I finalize these edits, you'll see after some delay these two will come on, and I'm going to clear that one just to make sure it's all reset. Now we can reset the whole thing. I will reset the whole thing and turn off, so all the inputs are turned off. Okay, I have everything reset, including the JSR added. So now I'm going to trigger in the new part with input 0. I'll leave it on long enough to get the full pulse. Latches on station 1.1. Now the part is traveling on the feed conveyor waiting for photo I2. I'll turn that on, and after some delay we see the extend proxies, and I'm going to turn photo I1 back off because I'm going to assume that when cylinder 2 is all the way forward, that photo I2 is not seeing the rod on the cylinder. We'll just assume that you mounted it physically so it looks underneath of the rod. So there we are. We now have the part pushed into the station. So you see how this logic works. You just take it one step at a time, and when you do it this way, it's not going to work out perfect. I can guarantee you. You will overlook something. But when you try to run the whole thing, you'll see the holes, and you go, oh, I didn't think of that. And you'll make whatever edits you need to make, and you'll be solid. We added a third rung of logic. I cleared everything so we can run it from the beginning. If you're looking at your virtual machine in your manual, photo I1 sees a part, and because our part number was less than 5,000, it's going on down the conveyor and on out. So let's put in a value here and do that again. Okay, now the part is traveling down the feed conveyor. However, we've latched station 1.1 and it's waiting for photo I2. So we'll turn on photo I2, and that extends cylinder 1 and cylinder 2. And once they are extended, they will trigger station 1-2. And I can see once again I don't have, in the main routine, I don't have a JSR instruction. What I do when I do these videos is, when I was originally doing the labs, I saved the .acd files. So I saved the files, I open them back up and use them. So evidently when I saved them, I did not have a JSR in here. We'll do this again. I'll try to do this in advance on the next one. Cylinders, and you will see that shortly these will latch station 1.2, turned on the drill motor, and after a 3-second delay to get the drill motor up to speed, then we latch a bit that extends cylinder 4, and we latch station 1.3. So we've seen a new part coming in. The part number was good for this station. When it hit photo I2, we extended cylinder 1 and 2. Once they were extended, we latched 1.2, which turned on the drill motor, and after 3 seconds to give it time to get up to speed, we extended cylinder 4 and then latched 1.3, station 1.3. That signifies that that step is done. Somewhere along the way, we added a reset rung to reset these bits to make it easier to do repeated exercising of your logic, rather than going back, right click, toggle bit to clear everything that you latch. Now you'll realize here eventually, if you haven't now, that latching logic isn't the best way to go, because when you latch bits or you use latches, then you have to, as we say, unlatch the whole world. In other words, you have to go back and make sure that you have logic that unlatches all those bits that you latched. For right now, if we push the reset button, then it clears the station 1 bits, it clears the virtual output bits, and it clears the real output bits. So let's scroll up here And these are the 4 rungs that we have in now. We're going to run these, and starting from scratch, Photo I1 sees some product, and because it was greater than 5,000, it latched 1.1. Now it's waiting for Photo I2. So we give it Photo I2, it extends, it sees it's extended, latches 1.2, turns on the drill motor. After delay, it extends cylinder 4, latches 1.3, and this is where we ran into a little problem. Notice that the cylinder 4 extended proc switch is going on and off. And that's because, and I had you go look at cylinders, so you could see that this is not really completing the logic. And that's because this rung up here is keeping this bit set so it's rerunning. In other words, if we're going to unlatch cylinder 4 extend solenoid, if we're going to unlatch this bit, but on the very next scan, this rung is still true and it latches it back up, then we're starting the retract all over again. Notice how it continues to run the delay retract. What we have to do is add logic to prevent this rung from executing more than once. In the manual, we had you add an instruction right here. So once this logic has been run, it doesn't unlatch these bits, but it can't latch this one back up, which we unlatched here. So now we're moving on ahead. So now we move to the next step. As we keep adding logic, follow the sequence. We've got all the way down to latching station 19. So I'm going to reset everything and start it again. Photo I1 sees a part, triggers the barcode reader. Now it's looking for Photo I2, which will turn that on until it sees the proc switches. Then back off. Drill motor extends cylinder 4. Then after a delay, we're going to retract cylinder 4. And when it's retracted, we turn off the drill motor, we retract cylinder 1 and 2, and we extend cylinder 3 to push out the part. And when cylinder 3 proc switch is made, then we start a delay retract cylinder 3. That's to allow the part to come to a stop on the finished product conveyor. Now notice that we added this fix in here identical to this fix up here. To prevent this from latching back up the extend solenoid after we unlatched it, we had to put this instruction in there. So this basically says if step 2 is complete and step 3 is not, then do this. But if step 3 is complete, don't do it again. We do the same thing down here with step 6. And we get all the way down here to step 8. The finished product conveyor is running. Now we're waiting for the part to show up at Photo I3. So we'll turn that on, which would be input 2. And that should cause the cylinder 5 to extend, and once we were extended, we turn off the finished product conveyor and we latch up 10. So far so good. So the only real, if you will, events that took place, and I see that our finished product conveyor is turning on and off. What we're observing with the bit in memory addressed as finished product conveyor, and you'll notice that local _4, you recognize that as one of our virtual output bits. But remember that whether it's a virtual output bit, like that one, or the one right below it that's a real output bit, local :1:0.data.3. Either way, they are both bits in memory. And the program, because it scans from top down, left to right, rung 7 is true, and it latches that bit, local_4.0.data.2. It is latched. Every single program scan. And then in rung 9, that rung is also true, and it unlatches that bit. So you have two conflicting instructions here. However, the outputs are going to be updated at the end of the scan. Now in this case, these aren't real outputs. Local_4, that's virtual outputs. And typically, to avoid any appearance of this situation, we buffer our I/O, meaning what you can't see here going on in the background is that the I/O is, its update in the memory of the controller is not synchronous with the program scan. Plus, what you're really seeing in this particular case is the graphics update. When this software, remember that this software is animating this graphic image that you're looking at. RSLogix does not exist except offline. You got to keep reminding yourself. I mean, it's okay to think of it as being what's in the controller, but the controller has something that is logically identical, but not graphically identical. You don't have ladder logic diagrams in the controller. So in order to allow you to monitor what's going on in the controller, you have an offline program that you're looking at. Right now we are looking at the offline program because there is only one ladder logic diagram program for you to look at, and that is the offline version. The difference is whether the state of the bits are being shown based on what's in the RAM of your computer or the RAM in the controller. Because we are online, then the state of all of these bits is being animated by the data in the controller. Logically, we are turning on that bit, local_4.0.data.2. We're turning that on, but in microseconds later, we're turning it back off. The only reason that you see it on here long enough for your eyeball to perceive it is because of the update time of the video. The communications between RSLogix 5000, RSLinks, and the controller catches it just right. You're going to see that it's showing the state of that bit is on. And it actually, that bit is turned on for a few microseconds and then right back off. So it's just a rare oddity. Now, again, this doesn't hurt anything, but it's something to keep in mind so you don't get confused. Now, notice that I added in a rung here. So I'm looking at that actual bit. If this bit was actually on, still on, when you get to rung 10, then it would latch this bit and it would stay latched. Now I've had this, see, you just saw it go on again. And this might show on, but it's the graphics, the GUI, the graphical user interface. You really need to make sure that you understand that what you're seeing on the screen here is little snatches of the state of those bits. And the only reason I'm belaboring this is because you could look at this bit right here showing that it's on and then going right back off. That could, strike some confusion and get you to believe that you have some sort of intermittent condition. If you want to say there's an intermittent condition, it is the timing of how the bits in the memory of that controller are being realized on this screen. If the communications happens to look at that bit at the right instant In other words, between this rung and this rung. There's microseconds between executing this rung, and this rung. So if the graphics happens to update when this rung has just been executed, it's going to show these bits as on. However, if they actually were on and staying on for any length of time that would affect anything, then this rung right here would latch that bit. And there is no instruction anywhere that's conflicting this bit. In other words, unlatching it, turning it off. This is what I call a bit trap. If I want to see if an actual memory address is going on and staying on effectively, then I use a bit trap. Now I'm going to drag this up to here and put it right before the rung where we unlatch it. See? And it trapped it. See, because I put it before the unlatch and after the latch. So if I put it in between these two rungs, it's showing, yes, it's on. You can see what we're doing here. We're kind of editing our code as we go, running the product through the system, and then whatever doesn't respond correctly, we make edits to correct it. And this is real typical for commissioning a project on the shop floor. As I've said before in these videos, you write logic that gets it close enough that you know you're not going to damage any of your equipment or wreck a bunch of expensive product, and then you start running it. And when you run into things like we did, remember we had a couple instances there where we had to go back and prevent a rung from re-executing the latch. So we're going to continue on. We won't follow the manual step by step. At this point, you should see exactly what's going on. We're only going to discuss what we did, and we're not going to do it in the detail and the laborious method that we went about it. Before we sequence this again, let's look at the rungs that we edited, rungs 7 and 8. We're not in a sequence right now, so station 1.7 is not set to 1. In other words, if you scroll up, you'll see that none of our steps are complete. However, let's assume that station 1.7 is complete. We have unlatched the bit that extended cylinder 3. Remember, cylinder 3 is the cylinder that pushes the finished part out onto the finished product conveyor. So if this were true and cylinder 3 was fully retracted, the reason we want cylinder 3 retracted, we don't want the conveyor to start up, remember, because the pusher on the end of cylinder 3 into stroke is V-shaped to keep the part centered as it pushes it out. If we were to allow the conveyor to start up the instant that cylinder 3 was extended, in other words, we use cylinder 3 extended procs to turn on the finished product conveyor, then the conveyor, along with the retracting pusher, would have a tendency to roll the part a little and may push it off to one side on the conveyor. We don't want to do that. Now, if you needed to speed up production and it didn't matter to you, then you could have the extended procs on cylinder 3 start the finished product conveyor, or you could use a timer that when the cylinder 3 extended procs went false, using a one-shot, so to speak, or just catching the trailing edge of the extended procs, you could start a time delay of a half second or so and then trigger the finished product conveyor, because you know that the pusher would have been pulled back from that finished part long enough. Here we have cylinder 3 retracted procs is made, and there is nothing in front of photo I3. Remember, photo I3 is on down the way on the finished product conveyor. And we want to know that cylinder 5 retracted procs is on. That tells us that cylinder 5 is retracted. So basically, the first condition there, cylinder 3 retracted procs, says that the part is clear of cylinder 3. The second not photo I3 says that there's nothing on the conveyor there. And the third one, Sonar 5 retracted proc, says that the stop is not sticking out there in the way. It's okay to turn on the finished product conveyor. I think you can see right away that if we turn on the finished product conveyor, as soon as the part gets to photo I3, then this rung is going to go false. But that won't turn off the finished product conveyor because, not at rung 7, because we latched this. If I haven't said it, I will say it now, that we will not continue with this latch type logic to the end of the manual. This is not the way we want to do it, but this is a typical way that people do program. And honestly, it doesn't work out very good, as you'll see. But it'll work. If you see somebody's program this way, don't get real critical towards them. Just work with it. We look at rung 8. And of course, if we turn on the finished product conveyor, then we've also latched station 1.8. And so if we go to rung 8, if station 1.8 is latched, that means that we started the finished product conveyor. When the part blocks photo I3, if we don't have a downstream call, meaning no one wants that part on down the way, then we will latch the extend cylinder 5 solenoid. We'll latch up that bit to extend cylinder 5 and latch station 1.9. However, if we do have a downstream call, then the true if off will not be true, the true if on will be true, and we'll latch 1.9, but we will not have extended cylinder 5. That will allow the part to keep right on going down the way to the next station. Once we completed step 9, in other words, we latch 1.9, which we would, once photo I3 is blocked, to sense the part, we're either going to extend cylinder 5 to stop the part, or we're going to let it keep on going. So if we go down to the next rung, in other words, station 0.9 is, that bit is latched. So in rung 9, if cylinder 5 is extended, then we want to stop the product conveyor, because we extended it because there was a part blocking photo I3. We don't want the conveyor to continue to run and wear the finish or mar the finish on the bottom of the part. However, if there is a downstream call, then we latch station 1.10. We latch the 10th bit. If we have a downstream call, when the photo eye sees the part, it's not going to do anything other than latch 1.9. And if we have a downstream call, microseconds later, it's not going to do anything other than latch 1.10. However, if we have a part there, and we won't have a part there, as you can see here, unless photo I3 is blocked and we extended the cylinder. Okay? If we do that, then we want to turn off the finished product conveyor like I said. So I basically was highlighting if we have a downstream call. Well, if we don't have a downstream call, then we're doing something else. Once we latch up 1.10, the 10th bit, if we have a downstream call and we have something blocking photo I3, then we retract cylinder 5. Now, this is not going to happen unless we have a downstream call. If we have a downstream call here and we didn't extend cylinder 5, well, unlatching that bit doesn't do anything. So really nothing, if we have a downstream call, nothing's going to happen here other than we're going to latch bit 11. And at this point, you see there is still a little bit more code that we could put in here, but now we're down at the jump to subroutine for the cylinders, the barcode reader, and here's our logic to clear these bits. So as you're running your logic, you can easily kind of reset the whole thing without going through and toggling a bunch of bits. One thing that we may not have mentioned is the barcode reader. We get a barcode trigger. Remember, that's up in one of the top rungs in the program. All that does is moves a value from the barcode buffer into the tag called part number. Now, this value is a value that you type in. In other words, we don't really have a barcode reader. We're pretending that this is our barcode reader. So when we get a barcode trigger, all it does is moves in, hypothetically, virtually, what it scanned off of that part. And it has to be more than 5,000 in order to run it through this station. Okay, jumping back in here, we've added a couple more rungs. Before we had bit 11 latching up, if we had a downstream call and Pt3 was blocked, because there's no reason to retract cylinder 5 unless there's a part there to go on downstream. Now you could retract cylinder 5 regardless if there's a downstream call, because if there's a downstream call, you want whatever parts are coming out as they come out. But we'll leave it the way it is. If bit 11 is latched up, then this will be true, and because we had a downstream call, we had a part in front of photo I3, and because we have a downstream call, we want to retract cylinder 5, retract the stop, and once it's retracted, then we turn on the finished product conveyor. Keep in mind, we don't want to turn on the finished product conveyor right away, because as the extend retracts, we don't want the conveyor to push the finished part against the stop and kind of spin it around the edge and move it out of the center of the conveyor. Once cylinder 5 is retracted, then we know it's clear. We turn on, we latch the bit to turn on the finished product conveyor, and we latch up bit 12 to saying that we finished step 12. And then once step 12 is set, we're simply waiting for a downstream call to turn off the finished product conveyor. And then of course, if that happens, then we can turn on bit 13 and then clear all of these bits to wait for another part to come along. Just as a review, we'll go up to the top here and go through these steps. See if we can cover whatever edits that we've done. New part comes in, photo I1. We initiate a timer data type, and the timer timing pulse gives the barcode trigger a 1 second pulse. Remember that the barcode trigger is right here in this routine, and it simply moves that value into part number. Once we latch that bit, we basically have said that we are expecting a part. In other words, if this is 5,000 or less, that won't get latched. So we'll say it's 55, 55, as you see in there. This bit gets set. If this bit is set, then we clear that part number, because we want to clear out that register for whatever the barcode reader reads, scans in the next part. And then of course we're going to extend cylinder 1 and cylinder 2, and cylinder 1 blocks parts coming from upstream. Cylinder 2 pushes it into the workstation. Once cylinder 1 and 2 are extended, we declare step 2 finished. So we latch the bit. Now here's where we added, if step 3 is already been set, then you can't run this rung again. You remember this. So right now this would be true. So when we set bit 2, we haven't done step 3 yet. That's what we're doing right now. We turn on the drill motor, and 3 seconds later we say that the drill motor is up to speed, and we extend cylinder 4 to bore the hole in the part, and we say step 3 is done. Step 3 is done. If cylinder 4 is extended, and remember, because of the adjustment of the proc switch, everybody does a little bit different. We want to put in a little delay to guarantee that it's fully extended into the part. And that gives us a little time to auger debris out of the hole. So when the 3 second delay is done, then we retract cylinder 4 and set bit 4, saying that step 4 is done. Step 4 is done. When cylinder 4 is retracted, we turn off the drill motor, and we retract cylinder 1 and cylinder 2 and say that step 5 is done. We could have a time delay on turning off the drill motor to allow the bit to cool. That's up to you. Okay, step 5 is done. Now here's another one of these. We put this in because if step 6 has already been executed or complete, we don't want this rung to latch up cylinder 3 again. Remember, cylinder 3 was oscillating back and forth. Step 5 is done, 6 is not done. Cylinder 1 and cylinder 2 are retracted. And the finished product conveyor is not running, because we don't want the finished product conveyor running when we push that part out onto the conveyor. So we latch up this to extend the solenoid to push the finished part out on the conveyor, and we say step 6 is done. And then coming down here, step 6 is done. Cylinder 3 has extended, and so we declare that there is a part at cylinder 3 extend, or the end of stroke, if you want, EOS, end of stroke of cylinder 3. And we give it a 1 second delay to compensate for any adjustment in the proc switch right here. In other words, if the proc switch got made early before it was fully extended, then we really don't want to start anything moving until it's fully extended. Once this 1 second delay is done, and you can make that delay anything you want. If you were really nervous about it, you can make it 5 seconds. Or if you didn't care about it, you could get rid of it or put in 0 for preset or something less. But that's what this little delay is for. We then retract cylinder 3. Notice we unlatch the extend solenoid, so it retracts, and we've done with step 7. With step 7 complete and cylinder 3 retracted, remember here we unlatch cylinder 3 solenoid, the bit that controls it, so it starts retracting. And remember, in our cylinder routine over here, we have all the logic that simulates the cylinders. When cylinder 3 retracted switch is made, if there's nothing in front of photo I3, remember that's on the finished product conveyor, and cylinder 5 is not extended, meaning that it's retracted. So instead of putting in not extended, we put in it's retracted. Turn on the finished product conveyor, we finish step 8. Okay, so the finished product conveyor is running now. When the part arrives in front of photo I3, the determination is whether or not there's a downstream call for that part. If there is a downstream call for that part, then it's going to set bit 9 and it's going to set bit 10 and keep on going through the logic. If there is no downstream call, then we're going to extend cylinder 5, and when cylinder 5 is extended, then we finish product conveyor. We've been through this recently. And here you see the rest of it. If there is a downstream call and photo I3 has a part in front of it, then we retract the solenoid. When the solenoid is retracted, then we turn on the finished product conveyor. And it runs until there's no downstream call. Now here's where it gets a little fuzzy. You're depending on the next station down, we'll call it packaging or cartoning, or maybe they're going to do another step on this. In other words, they're going to thread the hole in the part. It's up to them to tell you that there's no downstream call to allow you to turn off your conveyor. And then, of course, you've already seen this logic. Unfortunately, with this type of logic, written the way it is, where we latch the steps and we leave them latched, we cannot accept another part off of the feed conveyor with all of these bits latched up. And we're not going to clear station 1 bits until we set bit 13. And bit 13 won't get set unless the downstream call is turned off. So if we have a part sitting in front of photo I3 and no downstream call, then we're kind of sitting in rung 10 there. And then once we get a downstream call, we retract cylinder 5 and so on. But as long as there's this downstream call, we're not going to latch bit 13, and we won't clear the station 1 bit, so you can't run another part. So that's where we're going to go in our next video, is running more than one part through the system at a time.